Hi, Assalamualaikum and a very good morning. So today we're going to do some tutorial discussion for chapter 1 and we're going to focus on the subtopic of 1.3 stoichiometry. So in this video, we're going to cover tutorial question 2, 3 and 4 respectively. So without any further ado, let us start. So for question tutorial 2, we need to balance the following equation. So we are given the Cl2 aqueous and this is going to form ClO4 minus as well as Cl minus aqueous. And this happens in the basic medium. So you know that it is a redox equation and we need to use the ion electron method. And since we are talking about basic medium, in order for us to perform ion electron method, we're going to divide the equation, balance it, combine, and then we need to add OH once we finish step number 3. So for basic medium, we're going to do DBC OH. Okay, so for step number 1, divide, we're going to divide the equation first. So Cl2 can be converted into ClO4. At the same time, Cl2 can be converted into Cl minus. So they're going to be two equations, which is Cl2 aqueous becoming ClO4 minus, and Cl2 aqueous becoming Cl minus aqueous. So the most easier one is to look at the bottom one, which is, you know that the charge here is 0, and this one is negative 1. So you know that it will undergo reduction. Okay, because there's going to be a decrease in oxidation number. And when this one is reduction, this one automatically become oxidation. Okay, so once we divide the equation, we're going to do the balancing. So we're going to focus on this equation first, which is the Cl2 aqueous becoming ClO4 minus. So as what you can see here, the Cl here is 2, but the Cl here is 1. And therefore, we're going to add up number 2 here. Okay, so Cl on both sides are equal. But now, the oxygen here going to have O4 multiplied by 2, going to become 8. Okay, so here doesn't have any oxygen. So you need to add up 8 molecules of water. Okay, because as mentioned in the lecture, if oxygen, you need to balance it up with water. So 8 oxygen, and this is balanced on both sides. But now the number of hydrogen here is 16 because 8H2. So going to be 16 here. And as a result of that, we're going to balance it up using hydrogen plus ion. So how many should we add? We need to add as much as 16H plus because they're going to be 16 hydrogen here. So the hydrogen is 16. Okay. So the number of the atoms are now equal. So we need to look at the charges. So here they're going to be the charge here going to be 0, the total charge. But for this one, it's going to be negative 2 plus 16. So it's going to be plus 14. So in order to make sure that the charge is the same, we're going to add up 14 electron because 1 electron is negative charge, is 1 minus. So 1 minus times 14 is going to be negative 14. And as a result, the charge is going to be 0 as a whole. So the charge on both sides of the product side and the reactant side is the same. Okay. Now, we're going to do the balancing for the next equation. So we have Cl2 aqueous and then we're going to get the Cl minus. So Cl got 2 here, and as a result of that, we're going to add number 2 at the front here. In terms of charges, we have the Cl here going to be 0, and here we're going to get 2 minus. So in order to get the same charge, we need to add up electrons so that this area here going to get negative 2 as well. So the charge here is balanced as well. Okay. So once we have balanced both of this equation, we need to move on to the next step. Divide, balance, and then we need to combine. So the first equation that we have is Cl2 plus 8H2 liquid and these 2ClO4 minus 16H plus as well as 14 electrons. So we just copy it back again. But for this equation, Cl2 aqueous plus 2 electron becoming 2 chloride minus, we're gonna multiply that by 7 so that the number of electron is the same as the number of electrons here, because in order to combine we need to cancel out the electron and they need to be in the same number. So we're going to have 7Cl2, 14 electron and 14 Cl minus. Okay, so once we have the same number of electron, we can combine both of the equation together. So Cl2 aqueous plus 7Cl aqueous going to be 8Cl aqueous, because this one can combine together because of the same formula. And then 8H2 here going to just be copied back, the arrow copy back. And then we're going to have 2Cl4 minus aqueous plus 14Cl minus aqueous plus 16H plus aqueous. Okay, so you have basically settled B, B, C. And now you're going to do the O part, which is you need to add the number of hydroxide ions. So the number of hydroxide ion is added on both side of the which is on the left hand side as well as on the right hand side, and the number of hydroxide ion added need to be equal to the number of the H plus that we have. So in this case we're going to add 16 on the right hand side, and then we're going to add 16 hydroxide on the left hand side. Okay, because it needs to follow the same number of H plus here. So 16H plus and the H plus ions and hydroxide ion can combine together in order to form HOH, which is water, H2O here. So we have 16 of them, 16 of ions, and then we're going to have 16 H2O all together. So at the end, we're going to have 16 H2O liquid. And for the others, we just copy back again. Okay, so as what you can see here, we can further simplify it because you have 16 H2O on the product side and then you have 8 H2O on the reactant side. So you can cancel this one out, and as a result, this one gonna be 8, because 16 minus 8 you balance, it's gonna be 8. Okay, and you may look at this as a finished and balanced equation. And if you were to look further, actually this equation can be further divided by 2 in order to further simplify it. So 8Cl2 going to become 4Cl2 aqueous, and then the 16 going to be divided by 2 going to be 8 hydroxide ion, and 2 divided by 2 going to become 1, 14 divided by 2 going to be 7, and 8 divided by 2 going to be 4 H2O here. And this is the most simplified balanced redox equation that we can get. Okay, so for tutorial question 3, a reaction between 70 gram of copper 2 oxide, so the formula of copper 2 oxide going to be CuO, because you know that Cu2 plus with CO with O2 minus going to produce CuO, and 50 ml of 2.0 molar of nitric acid, so the nitric acid formula is HNO3, produces copper 2 nitrate, which given as here, as well as the water, which is the H2O. So for question 3a, we need to define the limiting reactant. So limiting reactant are basically a reactant that is completely consumed during a reaction and limits the amount of the product formed. Okay, and for question 3b, we need to write the balance chemical equation for the above reaction. So their hint here come from the question itself. So you know that the copper oxide gonna react with nitric acid, HNO3, and this gonna produce copper to nitrate, which is CuNO3 bracket 2, as well as H2O. Then we're also gonna write the phases. So copper oxide is a solid, nitric acid is an aqueous, copper nitrate is an aqueous, and H2O is a liquid. Okay, and now we try to count the number of atoms. So copper here 1 and copper here is 1, so okay. Nitrogen, so nitrogen here got 2 and 2, but here only got n 1 only, so we're going to put number 2 at the front here, so it's going to be 2n and also 2n. Hydrogen, we're going to have H2, so we got 2H, so balance. The oxygen, we're going to get 2 times 3, 6, plus 1 here. So it's going to be 0 oxygen, 7 oxygen. And here going to be 7 oxygen as well, because 2 times 3 plus 1 here. So this is a balanced chemical equation. And we can put nicely here. Copper oxide solid reacting with 2 mole of nitric acid aqueous in order to produce copper nitrate aqueous plus water. And for question C, we need to determine the limiting reactant. So we have two reactants, copper oxide and the nitric acid. So which of these two is the limiting reactant? In order to do that, we need to determine the number of mole of the copper oxide first. So the number of mole of copper oxide can be determined by dividing the mass of the copper oxide, 70, with the molar mass of the copper oxide, which is 79.6. So copper is 63.6, oxygen is 16, so 79.6. So 70 divided by 79.6, you're going to get 0.8794 mole that are available. And then you can also find the number of mole of the next reactant here, which is the nitric acid. So the number of mole of the nitric acid can be calculated using N equal to mV. Okay, because you know that it exists as an aqueous and it has a molarity. So the molarity is equal to the number of mole divided by volume. So the number of mole can be obtained by dividing the molarity with volume. So N equal to mV. So our molarity here is given as 2 molar. Okay, and our volume here is 50 ml, but then we convert that into liter, because you know that the molarity is in the unit of mole per liter. So liter and per liter can cancel out, and as a result, we're going to get 0.100 mole that are available. Okay, so we have found the number of mole of copper oxide and also nitric acid. But now we're going to see which one is the limiting reactant by using a stoichiometry. So let's say I can say that 1 mole of copper oxide going to react with 2 mole of nitric acid. If I have 0.8794 mole of copper oxide, then it's going to react with X. So my X here going to be 2 times 0.8794. And hence, the number of mole of the nitric acid that I needed is basically 1.7588. The number of mole that I need is 1.7588. But what I have here is only 0.1. So you know that the number of mole of nitric acid available is much lesser than the number of HNO3 needed. So you can say that the HNO3 is the limiting reactant. Okay, apa yang kita perlukan sebanyak ini, tapi ini je yang kita ada. Okay, so we know that this is the limiting reactant. Okay, moving on, for question 3D, we have to calculate the mass of the excess reactant after the reaction. So we know that our excess reactant is our copper oxide because we know that our nitric acid is our limiting reactant based on the previous question. So in order to do that, we need to compare the number of mole of HNO3 based on the equation, which is 2 mole of HNO3 react with 1 mole of CuO. So based on the limiting reactant number of mole, which is 0.1 mole of HNO3, then it's going to react with X mole of CuO. So in order to find X, it's basically a cross multiplication and the number of mole of CuO that has been used up during the reaction is 0.0500 mole of CuO. Okay, and you know that in the previous question, which is equation C, the number of mole of copper oxide available is 0.0794 mole. 0.8794 mole. Okay, but now in the reaction you have used up 0.05. So the excess reactant after the reaction you can calculate it by the number of mole available minus with the number of mole that has been used up. So 0.8794 minus 0.05, you're gonna get 0.8294 mole. Okay, so the mass of the copper oxide is basically mole times the molar mass. So the mole is 0.8294 multiplied by the molar mass of the copper oxide, which is 63.6 plus 16, 79.6. So once you calculated it, you're going to get 66.02 gram. So this is the mass of the excess reactant CuO after the reaction, because during the reaction you only use up 0.05. Now, for question E, we need to determine the percentage yield if the actual mass of copper to nitrate obtained from the reaction is 8.5 gram. So this one is the actual yield. Okay, hasil yang sebenar. So we need to find the theoretical yield. Secara teorinya, berapa yang patut kita dapat? So in order to do that, the 2 mole of HNO3 gonna produce 1 mole of copper nitrate here. So the number of mole of the nitric acid, which is the limiting number of mole, is 0.1, produces X mole. So you know that the number of mole of copper nitrate will be 0.05 mole of copper nitrate. And you can find the mass by multiplying 0.05 mole multiplied by its molar mass. So once you do the maths here, you're going to get 9.38 gram. So this one is the theoretical yield. Okay, so in order to find the percentage yield, you need to do a ratio between actual yield, which is 8.5 here, divided by the theoretical yield, which is 9.38, which is obtained from the stoichiometry. So percentage yield is equal to 8.5 divided by 9.38 times 100%. Okay, so this one doesn't have mole here per mole. So 8.5 divided by 9.38 gram, you're gonna get 90.62%. Okay, and this is how you're gonna find the percentage yield. For question 4, a sample of 1.55 gram of iron ore is dissolved in an acid solution in which the iron is converted to ferrum 2+. So basically, iron ore is dissolved inside an acid, and because it dissolved in acid for a very long time, it's gonna become ferrum 2+. Okay, and the solution is then titrated with KMnO4, which oxidizes ferrum 2+ to ferrum 3+, while the manganese O4- ions are reduced to manganese 2+ ions. So 92.95 ml of 0.02 molar of KMnO4 is required for the titration to reach the equivalence point. Okay, so from this situation, you know that you have ferrum 2 plus from the iron ore, and now this ferrum 2 plus gonna be titrated with KMnO4. Okay, so you have your burette, and then it is going to be titrated with KMnO4, and due to the titration, it's going to oxidize ferrum 2 plus into ferrum 3 plus. Meanwhile, the manganese ions are reduced to Mn2 plus. MnO4 minus ion are reduced into Mn2 plus ions. So the amount of KMnO4 is 92. The amount of neutralization needed is 92.95 ml, and then it requires 0.02 molar of KMnO4 in order to reach the equivalence point. Okay, so these are basically the idea. And now for A, we need to write the valence equation for the titration. So you know that this is a redox equation because there's going to be an oxidation as well as there's going to be a reduction as mentioned in the question here, oxidizes and reduce. So when we are talking about redox reaction, we are going to use ion electron method. Okay, and this ion electron method happens in acidic solution. So we're going to put here acid medium. Okay, and in order to do the ion electron method in acid medium, we're going to use the concept of DBC, which is divide, balance, and combine. So for the divide part, we're going to have two half equation, which is ferrum 2 plus into ferrum 3 plus, as well as from manganese O4 minus into manganese 2 plus. So this one is reduction, and this one is oxidation, as mentioned in the question. Now we're going to move on to the next part, which is balance. So ferrum 2 plus going to be ferrum 3 plus. So the number of atom, ferrum and ferrum, is the same. However, the charge is different. So we need to add one electron here so that the total charge plus 3 minus 1 going to be plus 2. So the charge going to be equal. For manganese O4 minus, you know that the number of manganese atom is the same, but here have 4 oxygen. So you need to add up with 4 molecule of water. Okay, so manganese 1, manganese here 1, oxygen 4, but now hydrogen here going to have 8. And as a result, you're going to add 8H plus. Okay, so the number of atom on both sides are basically equal. How about the charge? So the charge here is plus 2 because 0 and 2 plus. Here is plus 8 plus minus 1. So it's going to be plus 7. So you need to add up electron here so that the plus 7 can be reduced into plus 2. So we need to add plus 5 electron. So it's going to be negative 5, and overall it's going to be plus 2 on both sides. Okay, so this is the balancing for the manganese part. Okay, so once we have settled both the balancing part, now we need to go to the next part, which is to combine. And in order to combine, we need to ensure that the number of electrons for both half equation is the same. So we need to multiply the first equation here by 5. So it's going to be 5 ferrum 2 plus going to 5 ferrum 3 plus 5 electron. And for this one, we just copy back again. Okay, and in order to combine, you can cancel out 5 electron and 5 electron here. And this one, you just copy it back. 5 ferrum 2 plus MnO4 minus plus H plus. Same goes to here. Just copy back. 5 ferrum 3 plus Mn2 plus plus for water. Okay, and this is how you're going to do the balancing equation for the titration. You can even check the charge balance. So you can see that 5 times 3 plus 15 plus 2. So it's going to be plus 17. For here, you have plus 10 minus 1 plus 8. So overall, you're going to get plus 17 as well. Okay, so the charge are balanced. So the most important part here, you get this one correct, which is the balancing of the equation. So the balancing of the equation can be used to answer the next question, which is question B, which is to calculate the percentage of iron in the sample. So we have the equation just now, and now we need to find the percentage of iron. So iron here is mentioning the ferrum 2 plus, because you know that the iron ore is converted into ferrum 2 plus solution. So we are talking about ferrum 2 plus here. Okay, and in order to find the number of mole of ferrum 2 plus, we need to calculate the number of mole of manganese ion first, because this is what given in the question, which is the volume as well as the molarity. So mole of MnO4 is equal to Mv. So the molarity is 92.95. The molarity is 0.020, and the volume is 92.95 times 10 to the power of negative 3. Okay, so the molarity, the volume is as circled here, and the molarity is here. Okay, so the molarity is 0.02. The volume is 92.95 in liter, because we need to cancel out liter with per liter. So once you multiply that, you're going to get 1.859 times 10 to the power of negative 3 mole. From here, you can make a comparison from the stoichiometry. 1 mole of MnO4 minus will going to react with 5 mole of ferrum 2 plus. So 1.859 times 10 to the power of negative 3 going to react with 9.295 times 10 to the power of negative 3, because you're going to assume it as x and then you just cross multiply. So 5 times 1.859, you're going to get 92.95 times 10 to the power of negative 3. So in order to find the mass of the ferrum 2 plus, it's basically mole multiplied by the molar mass. So the mole of ferrum 2 plus is 92.95 and the molar mass of the ferrum is 55.9. So once you calculate that, you're going to get 0.5196 gram. Okay, and now the question asks us to calculate the percentage of iron in the sample. So the percentage of iron in the sample, you can calculate it by finding the ratio of the mass of ferrum 2 plus, which is 0.5196 gram, with the mass of the iron ore that is initially started in the that is initially dissolved in an acid solution. So 0.5196 divided by the mass of the iron ore, which is 1.55 times 100%. So once you do the maths, you're going to get percentage to be 33.52%. Okay, so I think that's all for this video. See you again some other time. Bye.